Good afternoon, everyone. My name is Sakar Joshi. I recently graduated with a degree in computer science from Bowling Green State University. This work was co-authored with my advisor, Dr. Shankar Das Roy, who is an associate professor in the Department of Computer Science at Bowling Green State University. The title of our talk today is Automated Extraction of Browser History from Computer Hard Disks. Further ado, let us go into the presentation. Before I even get into the technical details, let me set the scene with a scenario that motivated this work. Let's meet Alice. Alice is a trusted employee at Technocorp. She has access to all the sensitive patient records and proprietary tools. She starts researching computers online. She looks up how to transfer large files anonymously. She downloads compression and encryption tools, and the next morning she resigns. The company suspects something, so they hire a forensic investigator, Bob. Bob gets his hand on Alex's work computer, but now Bob checks the browser history database, a SQLite file sitting silently on the hard disk, and everything is there. Every search query Alice visited, every timestamp, the computator research, the file transfer tools, all of it. Reconstructed as step by step from browser history alone. Now, that's the power of browser history as a forensic artifact. Why browser history? Right? I give you three reasons. First, it reveals the user intent. Second, it builds a precise activity timeline. Every entry has a timestamp. You can reconstruct not just what someone did, but when they did it. Now, what's the problem? The problem is extracting that history today in this modern era is a messy, inconsistent, and time consuming process. Now, let's think about all the modern browsers out there. We got Chrome, Firefox as the major three browsers. They have different database schemas, different file structures, different table names, different timestamp formats. An investigator needs to know internals of each browsers separately. And on top of that, a single Windows machine can have multiple user accounts, and each user can have multiple browser profiles, like a work profile, a personal profile, a default profile, and that's a lot of ground to cover manually. Our research goal is straightforward. We want to automate this entire process from start to finish. We wanted a tool that could take a seized hard disk or forensic image as input and produce a complete organized browser history as output, without requiring the investigator to manually dig through all the file systems or understand the browser internals at all. But automation alone isn't enough. The tool also has to maintain forensic integrity throughout. So that means documenting everything, verifying that the evidence was never modified, and producing output that's defensible in court. This tool would have to be flexible as well. That means it has to work with different kinds of image formats out there that you might encounter in the field. So we came up with a solution, which is a Python-based two-stage pipeline. At the high level, stage 1 handles the disk image. It figures out what kind of image it's dealing with, establishes a hash baseline for integrity, and mounts the file system. Stage 2 does the actual browser analysis. It finds the users, locates the user browser databases, extracts the history, and exports everything. So there's no manual steps, no browser specific knowledge required from the investigator. If you point it at a disk image, it does the work. And here's the stage 1 pipeline. The input is a hard disk image. It could be a EWF or raw DD image or even a live system. Stage 1 starts by detecting what kind of input it's dealing with. For EWF images, which is a industry standard forensic format, EWF images are often split up across multiple files, E01, E02, E03, and so on. Given any of those segments, the tool automatically discovers and joins the rest of them. For raw DD images, the tool does the same thing. It detects and joins any segmented files out there. Once the image is open, the tool computes a baseline hash. The hash then is stored, and at the end of the pipeline, it's going to be recomputed and compared against the baseline. If they match, then it was never modified, and that's the chain of custody. And this is the stage 2 pipeline. Once the file system is mounted, stage 2 begins. Right? The tool opens the Windows users directory and enumerates all the user accounts on the system, filtering out the common system directories like all users, public, and all that. And for each real user account, meaning anything except those, it checks the standard app data paths where Chrome is and Firefox store their data. And for each of the installed browser, it then reiterates through all the user's browser's profile. Turns out a single user can have multiple profiles even for a single browser. So, for a single user, Alice could have two profiles for S, a work profile and a personal profile. The tool finds all of them. For each profile, it retrieves the main history database and critically the write ahead log file, which I'll talk about that later. The investigator can also specify a single browser if they need to, and the tool will just skip the rest. Now for the actual extraction. SQLite databases, which is what all three browsers uses, can't be read directly through the PyTSK3's interface. They need to exist as real files on disk before SQLite can actually open them. So the tool actually extracts all the database to a temporary directory first and then opens it. Okay, the WAL file that I mentioned, the write ahead log, has to be extracted alongside the main database with a matching file name. SQLite uses the WAL to hold transactions that might have been returned to log but not yet committed to the main database. Meaning, if you only extract the main database and ignore the WAL, the write ahead log, you miss the most recent browsing activity. So you have to extract both together. For Chromium-based browsers, Chrome NS, the tool queries the URL table, pulling the URL, page title, and the last visit time, while for Firefox, it queries most places table. Same fields, just different schemas. Timestamps are stored differently by each browser. Chrome NAS use Windows Epoch, microseconds from Jan 1 1601, while Firefox uses Unix Epoch in microseconds. So the tool converts both to a standard human readable format as well. And if the database is locked, which can happen on a live system, the tool catches the exception, logs it, and moves on rather than just crashing. Now, moving on to the output format, every extracted entry is standardized / normalized into the same structure: browser, profile, URL, title, timestamp. Here's an example. Here's a picture of an example which shows the JSON output. The tool actually imports it in two formats, CSV and JSON. CSV because if investigators who want to open it directly at the moment and sort it, filter it, or read it, they might need that. For JSON, if there's another tool that wants to integrate this later on, we want to keep this as an option as well. So this entry is case 3 test that I'm going to talk about. We can see how it detects for Firefox. It sees the recent URL timestamp and also the Wikipedia website. Now, for evaluation setup, we actually validated the tool against 3 test cases. It was case 1 is EWF image, case 2 is the raw data image, and case 3 is the live window system. Case 1 used an EWF image from 2020 Magnetaxiom CTF challenge. Now, across all the 3 test results, the results were consistent. Zero data loss, zero corrupted entries. We were able to recover complete metadata. Now, why would this all matter? Beyond just being a tool, right? For investigators, it means spending less time on mechanical extraction, more time on actual analysis. So the part that actually requires the human judgment. So this expertise barrier, uh, we this tool tries to remove it. You don't need to know Chrome's internal database schema. You don't need to know how Firefox formats its timestamps, how Edge stores its profiles. The tool handles that. It also produces a consistent, documented, and reproducible logs along with the outputs in a CSV and JSON format. These results would hold up in court because they are consistent, they are verified with the checksums, and we know that the tool doesn't modify any entry. Now, moving on to limitations. Just want to be upfront about what the tool cannot do right now. For encrypted file systems are out of scope. Sorry about that. Yep. Also, it's a functional prototype. It works as a evaluation shows, but it hasn't been hardened to a level you would expect from a production forensic platform. This Python pipeline automates the extraction of the images and also the live window system, maintains full forensic integrity and chain of custody logging, validates it, and ensures that it has been untouched throughout the analysis. It is a validated tool against real forensic images and a live system and has given complete accurate results in every cases. The source code is publicly available on GitHub, and we hope it's useful to forensics community. All right, that's the end of our presentation. I would like to thank Dr. Roy for his guidance throughout this project, and thank you all for your time and attention. If you would like to reach out, let us know. Our email's right on the screen. Our GitHub links right here. You'll find it in our GitHub repos.